Hey future seekers, tonight we begin with a journey that stretches across the vastness of space and time into the quiet mysteries that glide silently through our solar system. Our guide tonight is a visitor from the depths of interstellar space, a mysterious and elongated icy traveller named 3I/ATLAS. Its journey is slow and deliberate, and our exploration tonight will gently consider what could be the most extreme possibilities. Before we settle in and begin our peaceful journey into the future, take a moment to like this video and subscribe, only if what I share here truly resonates with you. Your support helps me create more of these stories, and if you feel like it, let me know where you're tuning in from and what time it is. It's always fascinating to see the many corners of the world where we connect. Now, dim the lights, make yourself comfortable, and let's ease into tonight's journey together as we explore what lies ahead. Chapter 1. The Silent Wanderer. Understanding 3I/ATLAS. As we begin, imagine the vast darkness of space stretching endlessly around us. The silence so profound it feels almost tangible. In this quiet void drifts 3I/ATLAS, a small elongated comet, its surface irregular and jagged, glowing faintly under the distant light of the sun. It has travelled for millions of years, passing stars, clouds of cosmic dust, and the gravitational pull of unseen planets. Scientists first detected it in October 2017, and what immediately captured their attention was its trajectory. It did not originate from our solar system. Unlike comets born here, orbiting predictably around the Sun, 3I/ATLAS is an interstellar wanderer, a traveller from a distant star system, making a fleeting visit through our cosmic neighbourhood. Its elongated shape is unlike any comet we have studied, stretching perhaps hundreds of meters from end to end. Its surface reflects very little light, giving it a dark, mysterious appearance, almost like a shard of space rock painted with cosmic shadows. But what can we truly say about it? Astronomers study its motion, rotation, and trajectory to learn what it can teach us about other parts of our galaxy. Its path is a story of millions of years of silent travel. Every twist, every rotation carries information about distant worlds and the forces that shape them. Now, let your mind drift slowly with me. Picture a small speck moving silently through an enormous sea of stars. There is no sound, only the gentle dance of gravity pulling and shaping its path. Its journey reminds us of how vast and ancient the universe is, and how fleeting our own place within it might feel. In this chapter, our focus is understanding the comet not as a threat, but as a messenger. By observing it, we can learn more about cosmic formation, the materials that make up distant star systems, and even hints about the origins of life elsewhere. Scientists study its colour, its rotation, and the faint dust and gas trailing behind it, each measurement bringing us closer to understanding the visitor from the stars. Even in the worst-case scenario, if, hypothetically, it strayed from its predicted path, the vast distances involved make any direct threat incredibly unlikely. But tonight, as we drift into thought and imagination, we will explore those possibilities gently, without fear, with curiosity as our guide. So, settle deeper into your seat, breathe slowly, and let your thoughts float alongside this silent traveller. Picture yourself gliding through the emptiness of interstellar space, watching 3I/ATLAS spin silently, a relic of distant worlds carrying secrets older than our sun. Chapter 2. Watching a Cosmic Visitor. As we continue our quiet voyage, let us shift our focus from the comet itself to the careful, patient methods scientists use to study a visitor like 3I/ATLAS. Imagine a naturalist observing a rare bird from afar, Every movement, every sound is noted with attention and care. Astronomers approach their work the same way, collecting faint light, measuring motion, and reading the subtle signatures of atoms and molecules. Each instrument is like a different eye or ear, sensitive, methodical, and precise, and together they form a gentle chorus of information that slowly tells the comet's story. The journey began with a survey telescope, a vigilant watcher of the night sky, scanning for anything that moved against the backdrop of distant stars. On July 1st, 2025, the Atlas system in Chile flagged a small, moving smudge. That smudge would soon be confirmed as an interstellar comet, a visitor from beyond our solar system. Across the globe, scientists quietly redirected their telescopes, requested observation time, and began filling a calendar with a carefully orchestrated sequence of measurements. These early surveys act as the sentinels of the sky, patient and constant, always recording the universe's subtle motions. From these initial observations, larger and more precise instruments took over. Space telescopes like Hubble and James Webb offered views unobstructed by Earth's atmosphere. Hubble's sharp eye captured detailed images of the comet's hazy coma and dust cloud, allowing scientists to measure how much material was lifting off the nucleus and estimate its size. These images were more than just beautiful. They were maps of movement, light, and structure, analysed pixel by pixel to uncover the comet's physical characteristics. Hubble revealed a teardrop-shaped dust cloud surrounding the nucleus, providing a deeper understanding of its form and activity. Complementing these visual observations, the James Webb Space Telescope employed infrared spectroscopy to read the chemical fingerprints hidden in the comet's light. By splitting the light into a rainbow far beyond human vision, Webb revealed absorption and emission lines from molecules like water, carbon dioxide, and carbon monoxide. In the case of 3I/ATLAS, infrared data showed an unusually strong carbon dioxide signal compared with water, a clue to the comet's origins. Perhaps it formed in a cold, CO2-rich region, or perhaps cosmic radiation over billions of years altered its surface. Spectroscopy, like patient chemistry applied to the sky, provides these gentle insights. Ground-based observatories also contributed vital information. Large optical telescopes, such as those in the Gemini and Noir Lab networks and the Rubin Observatory, monitored brightness changes, rotational speed, and the development of tails. Instruments measuring precise positions, astrometry, allowed scientists to calculate the comet's trajectory. By recording its position against background stars over multiple nights, astronomers determined that 3/ATLAS follows a hyperbolic path, meaning it is not bound to our Sun and is merely passing through. These calculations reassure us. The comet's path keeps it safely distant from Earth. Sometimes even more specialized instruments join the effort. Missions like SPHEREX, surveying the sky in infrared wavelengths, provide complementary spectral coverage, enriching the portrait of the comet. Coordinated observations across space telescopes, ground observatories, and survey missions transform a brief celestial visit into a rich, multi-dimensional record. In the case of 3I/ATLAS, this global network has been quietly activated, capturing as much data as possible before the comet drifts back into interstellar darkness. This kind of science is both challenging and meticulous. The comet is faint, moving quickly against dense star fields, and its dust can obscure the solid nucleus. Observing windows are limited. Sometimes the best views occur when the comet is near the Sun from Earth's perspective, making ground-based observation difficult. Scientists overcome these challenges by combining data from multiple wavelengths and modelling physics, dust dynamics, sublimation rates, and changes in coma brightness caused by sunlight. Every measurement is deliberate, every calculation precise. Consider a quiet human moment. A night shift astronomer in a dim control room, tea cooling beside them, watching an automated alert. There is no drama, only calm efficiency. They prepare sequences of observations, coordinate with colleagues worldwide, and type notes into a shared log. Slowly, a chorus of telescopes responds, each adding its gentle voice, a measurement here, a spectrum there, until a fuller picture emerges. This patient mosaic of data is not about alarm, it is about understanding. And when it comes to assessing risk, these methods are exactly how astronomers evaluate potential hazards. Precise orbit calculations, chemical analysis, and continuous monitoring allow scientists to quantify probabilities accurately. For 3I/ATLAS, the best orbital solutions, confirmed by multiple observations, make any dangerous approach to Earth effectively negligible. This certainty allows agencies to focus calmly on the extraordinary opportunity, a rare visitor from another star system, offering insights into worlds far beyond our own. As this chapter draws to a close, picture the global network of instruments quietly at work, whispering in different languages of light. Scientists exchange measurements in steady, careful cadence. Together, they transform a faint, distant comet into a rich source of knowledge and wonder. In the next chapter, we will explore the chemistry revealed by these instruments, the surprising dominance of carbon dioxide in 3I/ATLAS's coma, what it might tell us about the comet's origin, and how these chemical fingerprints expand scientific imagination without inciting fear. Chapter 3: Cosmic Chemistry, Unveiling the Secrets of 3I/ATLAS. Imagine, once again, the endless expanse of space. In this silence drifts 3I/ATLAS, carrying with it the faint whispers of its home system, encoded in the gases and dust that surround its dark, elongated core. The coma, that halo of escaping gas and dust illuminated by distant sunlight, is the comet's way of telling its story. Through careful observation, scientists can read that story, molecule by molecule. Infrared spectroscopy, the method we introduced in the last chapter, allows astronomers to detect the specific wavelengths of light absorbed or emitted by molecules. Each molecule has a unique fingerprint. Water, carbon dioxide, carbon monoxide, and more exotic organic compounds each leave subtle traces in the light. For 3I/ATLAS, one of the most intriguing findings has been the unusually high abundance of carbon dioxide relative to water. In our solar system, most comets show water as the dominant volatile compound. Water sublimates, turning from ice into gas as comets approach the Sun. But 3I/ATLAS challenges that pattern. Its coma is richer in CO2, suggesting it formed in an environment very different from the familiar cold regions of the early solar system. Perhaps it formed farther from its parent star, where temperatures were low enough for CO2 ice to condense but water ice was less prevalent. Now picture the comet as a cosmic messenger carrying ancient frozen material from another star system. Its dust grains contain silicates and possibly complex organic molecules, tiny remnants of the protoplanetary disk from which it originated. Each particle is a tiny time capsule, unchanged for millions or even billions of years. By analysing these grains, astronomers can infer the conditions of distant planetary systems, giving us a glimpse into how other worlds form, evolve, and perhaps even develop the ingredients for life. Consider the gentle way sunlight interacts with 3I/ATLAS. As the comet moves closer to the Sun, sunlight warms its surface, releasing trapped gases. These gases expand and escape into space, forming the visible coma. Tiny dust grains are carried along, creating the long, streaming tail. This process is natural, peaceful, almost meditative when visualized in slow motion, an interstellar traveler slowly shedding fragments of its story into the void. Interestingly, some of the molecules detected are rare in comets from our solar system. Compounds such as diatomic carbon, C2, and certain hydrocarbons indicate chemical processes unique to its home system. By studying these, scientists can compare chemical diversity across the galaxy, learning whether our Sun's neighbourhood is typical or unusual. In a way, 3I/ATLAS acts as a floating library, offering pages of chemical data from another corner of the galaxy. Now let us gently imagine a thought experiment. What if this comet contained a trace of prebiotic molecules, the very compounds that can form amino acids, the building blocks of life? While the probabilities are low, it is scientifically plausible. Comets in our own solar system have delivered organic molecules to Earth, and by analogy, interstellar comets could carry ingredients for life across stellar distances. Every observation of 3I/ATLAS deepens our understanding of the raw materials available in the galaxy. The chemistry also guides models of the comet's origin. With CO2 dominating the coma, scientists estimate that the comet likely formed in a cold outer region of its original star system. Cosmic radiation over millions of years could have altered some of its surface compounds, darkening its surface and creating the low reflectivity we observe today. Each measurement, each spectral line, is a brushstroke in a picture slowly emerging of a star system we may never visit. From a calming perspective, consider the comet as a quiet teacher. It drifts past our solar system without threat, offering knowledge in a serene, unassuming manner. Its journey reminds us of the vast diversity of the universe and the gentle rhythms of cosmic evolution. Nothing rushes here. Molecules slowly sublimate, dust drifts away, and we watch, learning to be patient observers of a grand, slow-moving universe. In the next chapter, we will explore the trajectory and dynamics of 3I/ATLAS, tracing how it moves through space and how gravitational interactions guide its path. We will examine its hyperbolic orbit, its rotation, and the physics of a body moving freely from another star, all while maintaining a soothing, meditative pace. Chapter 4. The Path of a Wanderer. Trajectory and motion of 3I/ATLAS. Imagine once again the vastness of space. The darkness stretches infinitely in every direction, punctuated only by distant stars that twinkle softly like faint, faraway lanterns. In this quiet expanse, 3I/ATLAS drifts, moving along a path that is both precise and mysterious, guided by the immutable laws of gravity and motion. Unlike comets born in our solar system, which trace elliptical orbits around the Sun, 3I/ATLAS follows a hyperbolic trajectory. Its path is open-ended, a fleeting visit through our solar neighbourhood. Picture an archer's arrow, fired from a distant bow, gliding smoothly through the air in a single unbroken arc. Once released, it cannot return. Its journey is continuous, carrying it ever onward. Astronomers have calculated its velocity with meticulous care. 3I/ATLAS moves at tens of kilometers per second relative to the Sun, fast enough to traverse the distance from Earth to the Moon in mere minutes. Yet, in the silence of space, this speed feels almost imperceptible. The comet glides without sound, without turbulence, a serene traveller weaving through the fabric of space. Its elongated shape affects its rotation and tumbling. Unlike a perfectly smooth sphere, This shard-like object spins irregularly, gently turning as it drifts. The rotation can create subtle variations in the sunlight it reflects, causing the brightness seen from Earth to fluctuate slightly. These variations are not alarming, they're natural, a reminder that the universe is alive with motion, even in stillness. Gravity plays its part with quiet elegance. Every planet, every moon exerts a tiny tug on the comet, subtly altering its path. Even the distant gas giants, Jupiter and Saturn, have a minute influence, nudging the comet imperceptibly as it passes. Astronomers model these gravitational interactions carefully, ensuring that they understand every turn and twist of its journey. Through these calculations, they can predict its closest approach to the Sun and the distance at which it will leave our solar system. Now, let's slow down and visualize this. A comet moving through the inner solar system, the Sun illuminating one side as it passes, planets bending its path ever so slightly, and its own rotation creating a soft flicker of reflected light. Dust streams gently from its surface, forming a tail that lingers and stretches across millions of kilometers. This tail is not a threat. It is a natural consequence of warmth and motion, a cosmic brushstroke painted by sunlight itself. Hyperbolic motion has fascinating implications. Because 3I/ATLAS is not gravitationally bound to the Sun, it will eventually escape, returning to the emptiness of interstellar space. It has come from an unknown star system, travelled perhaps millions of years across the galaxy, and will continue its journey long after our Sun has faded. Its brief visit is a whisper of the vastness beyond, reminding us of the immense scale of time and distance in the cosmos. Astronomers also study its trajectory to anticipate what might happen in the extremely unlikely worst-case scenario. Even if small fragments were to separate from the comet, or if an unobserved gravitational interaction occurred, the distances are so vast that the probability of Earth impact is negligible. In this sense, understanding its motion is not only a scientific exercise, it is a lesson in perspective, teaching patience, observation, and the calm certainty of physics. Consider for a moment the human element again. Observatories around the world track the comet night after night, collecting images, measuring positions, and refining models. Scientists review calculations, check for errors, and slowly build confidence in their predictions. This process is deliberate and methodical, a meditation on certainty amidst the immensity of space. There is no rush, no panic, only careful observation, analysis, and respect for the natural rhythms of the universe. The gentle dance of gravity and motion also explains the comet's orientation as it passes. Tidal forces, the push and pull of solar radiation, and its own rotation combine to determine how gas and dust escape, shaping the coma and tail we observe. This is why each observation of 3I/ATLAS is unique. Its appearance changes subtly over days and weeks, providing a living record of physics in motion. As we drift through thought alongside 3I/ATLAS, we begin to appreciate the beauty of its path. Every second of motion is governed by elegant equations, every twist and spin an expression of cosmic harmony. It passes silently, peacefully, leaving behind a trail of dust and knowledge, a gentle reminder of the quiet order that permeates the universe. In the next chapter, we will explore the potential scientific insights this comet offers, including what it can reveal about the origins of star systems, the diversity of planetary formation, and even the distant possibilities of life beyond our own solar system. We will continue our journey with calm curiosity, discovering how a small interstellar wanderer can expand our understanding of the galaxy. Chapter 5. Lessons from Afar. What 3I/ ATLAS reveals about other worlds. Picture again the silent expanse of space, where 3I/ATLAS drifts slowly, a solitary traveller from a distant star system. Its journey is long, measured in millions of years, and each fragment of ice and dust it carries is a silent messenger from a world far beyond our own. As it passes through the solar system, scientists have an extraordinary opportunity, a glimpse into the composition, chemistry, and history of a planetary system we may never visit. By analysing the light reflected and emitted from 3I/ATLAS, researchers can reconstruct aspects of its home system. Its unusual chemical composition, particularly the high proportion of carbon dioxide relative to water, suggests that the comet formed in a cold, outer region of its original system. Perhaps it originated in a zone far from its parent star, where solar radiation was weak and temperatures allowed certain volatile ices to condense while others remained frozen. Dust grains carried within the comet are equally revealing. These tiny particles, often smaller than a millimetre, contain silicates, metals, and organic molecules, the building blocks of planets and, in some cases, life itself. By studying the ratio of these elements, astronomers can infer how planets may have formed around that distant star and how different its environment was compared to our own solar system. It's a subtle but profound connection. Through one small, silent object, we touch the distant history of another world. Consider too the comet's trajectory. Hyperbolic comets like 3I/ATLAS are rare visitors. Most comets in our solar system remain bound, orbiting the Sun in predictable ellipses. Interstellar comets, however, come from afar and are on one-way journeys. Each one offers a unique laboratory, a sample of material formed in a completely different environment, untouched by our Sun's influence until its brief passage through our neighbourhood. It's almost as if the universe itself is sharing a quiet story with us, fragment by fragment. Astronomers use sophisticated models to analyse what these observations mean. By combining spectral data with measurements of dust and gas output, they can estimate the temperature, density, and even the radiation history of the comet. These clues tell a story of long-term exposure to cosmic rays, perhaps billions of years of slow chemical evolution, a subtle record written in ice and rock. Now imagine the possibilities this knowledge opens. By comparing interstellar comets with the comets in our own system, scientists can begin to identify patterns. What elements are common across star systems? Which chemical pathways are universal? And which environments might be conducive to forming planets capable of supporting life? Each comet is a test case, and 3I/ATLAS, as a visitor from an entirely different system, is among the most valuable. Even more intriguing are the organic molecules within 3I/ATLAS. While the comet has not been directly sampled, spectral analyses suggest the presence of hydrocarbons and potentially prebiotic compounds, molecules that, under the right conditions, can form amino acids, sugars, and other precursors to life. These molecules are widespread in space, but finding them in an interstellar comet suggests that the raw ingredients for life may be more universal than previously thought. It is a gentle, humbling reminder that the building blocks of life are not confined to Earth. They float quietly among the stars, waiting for the right conditions to assemble. Let us pause and visualize this. The comet drifts past the Sun, its faint tail trailing behind, and within it lie atoms and molecules that have existed since the birth of its parent star system. These materials have survived the intense radiation of interstellar space, collisions with cosmic dust, and the gravitational pull of countless celestial bodies. And now, by observing them with careful instruments, we gain knowledge, not through noise or spectacle, but through patience, precision, and calm observation. This chapter also invites reflection on the scale of the universe. Each measurement of 3I/ATLAS connects us to events that occurred billions of years ago, in star systems light years away. We are, in a sense, students of time and space, reading a manuscript written in ice and dust. The comet's passage is brief, yet its information is enduring, offering insights that may inform our understanding of planetary formation, stellar chemistry, and even the potential ubiquity of life in the galaxy. Finally, the knowledge gained from 3I/ATLAS is a reminder of human ingenuity and patience. Teams of astronomers, engineers, and analysts around the world coordinate observations, share data, and slowly piece together the comet's story. They do so without urgency or alarm, with the steady rhythm of curiosity and the desire to understand. In this calm, methodical way, 3I/ATLAS teaches us about science, the universe, and our capacity to learn from the quiet whispers of distant stars. In the next chapter, we will gently explore the potential interactions of 3I/ATLAS with the solar system, including its minimal influence on planets and other objects, and why even its closest passages are peaceful rather than threatening. This will further enhance our understanding of the comet as both a scientific treasure and a serene traveller through space. Chapter 6, 3I/ATLAS and its subtle effects on the solar system. As we continue our journey alongside 3I/ATLAS, imagine it gliding through the solar system like a silent traveller, a solitary shard of another star system, moving gracefully through familiar territory. Despite its rapid speed and interstellar origin, its interactions with our solar system are subtle, almost imperceptible. The laws of physics govern its path with quiet elegance, ensuring that even in close approaches the effects are minuscule. First, let us consider the forces acting on the comet. Gravity is the primary influence, pulling it gently toward the Sun as it approaches perihelion, the closest point in its orbit to our star. Every planet exerts tiny gravitational tugs, but the vast distances and the comet's high velocity ensure that these forces merely nudge it slightly, rather than dramatically altering its path. Unlike a spacecraft guided by engines, 3I/ATLAS moves entirely under the natural forces of the cosmos, its motion dictated by inertia and gravity. Now, picture the comet passing near the outer planets, Jupiter, Saturn, Uranus, and Neptune. Even here the effects are gentle. The comet is small compared to the massive planets, and although it may create subtle gravitational perturbations in nearby dust or small objects, the distances are enormous. The planets themselves remain largely unaffected, continuing their slow, predictable orbits around the Sun. From Earth's perspective, the comet's journey is almost entirely observational, a passing whisper in the solar system's vast symphony. But what about dust and gas? As 3I/ATLAS nears the Sun, sunlight warms its surface, releasing gases like carbon dioxide and small particles of dust. These tiny emissions form the coma and tails we observe from Earth, yet the quantities are extremely small relative to the scale of the solar system. The material disperses into space without impact, carried along by solar radiation and the solar wind. Even if Earth were aligned with the tail, which it is not, the effect would be imperceptible. Still, let us gently explore the hypothetical worst-case scenario. What if a fragment of the comet were to break off on a precise trajectory toward Earth? Even here, the risk is extraordinarily low. Interstellar comets like 3I/ATLAS are moving at tens of kilometers per second, which means any fragment would require precise alignment to intersect our planet. The vast emptiness of space makes such an event almost astronomically improbable. Scientists run computer simulations to calculate these probabilities, and the results confirm what observations suggest. A direct impact is extraordinarily unlikely. Another theoretical concern could be gravitational perturbations of smaller solar system objects. Could 3I/ATLAS alter the orbits of asteroids or comets in a way that later affects Earth? Again, the answer is reassuring. The comet's mass is tiny compared to planets or large asteroids. Its gravitational influence, while measurable with sensitive instruments, is negligible in practical terms. It may cause a subtle shift in a distant object's orbit over millions of years, but these are changes so slow and minor that they present no immediate danger. Now, picture a more extreme scenario: a dense, unseen companion fragment travelling along with 3I/ATLAS. Astronomers account for such possibilities by tracking the comet with high-resolution telescopes and modelling its potential debris field. So far, no such companion has been observed. The comet appears solitary, a single elongated object silently tracing its hyperbolic path. The data reassures scientists and the public alike. Even the worst-case scenarios are overwhelmingly improbable. Beyond hypothetical risks, there is a more positive, profound effect of the comet's passage. Its presence allows scientists to test our ability to respond to unexpected interstellar visitors. Every observation strengthens our models, improves our instruments, and teaches us patience and precision. In this sense, the comet's journey is both a scientific treasure and a quiet rehearsal for handling more complex objects in the future. So, let us return to a meditative perspective. Imagine watching 3I/ATLAS from a distant hill or through a telescope. You see a small dark object against the backdrop of distant stars, moving silently, a traveller from another galaxy. It leaves behind a faint glow, a whisper of gas and dust, and then continues onward, unaffected by the planets it passes. There is no threat, only curiosity, knowledge, and the quiet wonder of observing something entirely foreign yet gracefully integrated into the natural flow of the solar system. In the next chapter, we will explore the tools and simulations used to assess the extreme worst-case scenarios of interstellar objects, including how astronomers calculate probabilities of impact, debris fragmentation, and gravitational effects, all presented in a calm, digestible, and reassuring way. Chapter 7. Counting the Improbable. Risk Assessment and Simulation for 3I/ATLAS. As we continue, let us sit with the quiet work of prediction, the slow, careful art of assessing risk. When an unfamiliar object passes through our skies, risk assessment is not about alarm, it is a practice in measurement, modelling, and imagination constrained by data. For 3I/ATLAS, scientists ask a single careful question. Given what we know, how do we translate uncertain observations into trustworthy probabilities? At the heart of this practice are simulations, many, patient, and varied. Imagine a room full of computers, each running a slightly different version of the comet's future. These are not dramatic forecasts but calm experiments. Change a small parameter here, nudge an angle there, and watch how the path unfolds. Together, these runs form a statistical picture. The technique most commonly used is an ensemble approach. Thousands, sometimes tens of thousands, of simulated trajectories are computed, each one sampling the range of uncertainty in measurements. Collectively, they reveal how likely different outcomes are. The bulk cluster that leads to safe passage, and the vanishingly small tail that produces unusual rarer results. One key input to any ensemble is astrometric uncertainty, the tiny errors in positional measurements. Every telescope observation has limits. background stars, atmospheric blurring, faintness of the target. When scientists combine many observations, they can shrink that uncertainty, but never entirely remove it. Thus, each simulation begins with slightly different initial positions and velocities that reflect those observational uncertainties. Over many runs, the spread of resulting trajectories tells us how confident we can be in the comet's future path. Another important factor is non-gravitational forces. Unlike a rigid rock, comets outgas. They release gas and dust as sunlight warms volatile ices. This sublimation produces tiny thrusts, changing the object's motion by small amounts. For a slowly drifting visitor, these forces can be modelled and often constrained by observing changes in brightness and tail structure. In simulations, scientists include parameterized models of outgassing to see how these gentle pushes might alter the comet's path over weeks and months. Generally, these effects are subtle, but they are included because thoroughness is calming. It reduces unknowns and narrows the range of plausible outcomes. When fragmentation is considered, the simulations become more complex and beautifully careful. Comets are often porous aggregates rather than solid monoliths, and they can shed pieces when stressed by heating or tidal forces. To model this, researchers create fragmentation scenarios. A primary body splits into many pieces, each assigned slightly different velocities and sizes. Simulations then track each fragment's path. The result is not catastrophe, but complexity. A cloud of trajectories with some dispersion. Most fragments drift harmlessly away. A tiny subset could, in principle, follow a path intersecting a planet. The statistical tools transform these many possible stories into a single, comprehensible statement about likelihood. Scientists also run n-body simulations that account for the gravitational nudges of planets, moons, and the Sun itself. These calculations are patient and precise, integrating the motion of the comet and any fragments forward in time, while the computer quietly tallies the outcomes. Because the solar system is well measured, these models are robust. They capture how tiny tugs add up across days and weeks, and they show how likely it is that a chain of nudges could produce an unusual encounter. For 3I/ATLAS, such models consistently place the most probable outcome in the realm of safe passage. Another layer of simulation concerns atmospheric entry physics, but only relevant for the extremely unlikely case of a fragment being placed on an Earth-crossing path. Here, specialists simulate how a meteoroid would behave entering an atmosphere, how it decelerates, whether it breaks apart high above the ground, and how much energy it would deposit into the air. The results typically divide outcomes into two comforting categories: a high-altitude airburst that spreads energy harmlessly across the sky, or a ground impact that, depending on size, might create a localized effect. These models rely on decades of experience from natural meteors and carefully validated physics, not on speculation. They allow authorities to plan sensible responses rather than reacting to fear. A quiet tug in these risk estimates is the size distribution of fragments. If, in a hypothetical breakup, most fragments are tiny dust and small pebbles, their entry would be benign, producing meteoric streaks across the sky. If, hypothetically, a fragment were as large as a city block, the dynamics change, but the simulations that produce such a fragment on a direct collision path must overcome many improbably precise alignments. Risk assessment therefore consistently shows a dramatically declining probability as the potential impact consequence increases. In other words, small, harmless events are far more likely than large, damaging ones. Monte Carlo methods give us not just probabilities but also confidence intervals, ranges that state how certain we can be. Scientists prefer to speak in these ranges because uncertainty is honest and calming. It tells the listener exactly how much is known and how much remains unknown. For 3I/ATLAS, confidence intervals around its closest approach place Earth well outside the narrow zones that would concern impact specialists. The ensemble of simulations run and rerun as new data arrives gradually tightens these intervals. With each new observation, the range of plausible paths narrows like a slow, peaceful focusing. There's also a practical human side to these simulations. International teams exchange data in the quiet hours of the night, sharing updated astrometry and photometry. The modelling groups rerun ensembles with fresh inputs. Updates are circulated in calm bulletins, and advisory groups review results to determine whether any action, such as more intense observation campaigns, is needed. This coordinated, disciplined cadence is part of why alarm is unnecessary. The system of observation, simulation, and review is well practiced and designed to manage rare events calmly. Finally, let us consider mitigation in purely hypothetical terms, not as instructions, but as the reflection of reasoned planning. If simulations ever identified a credible, non-negligible chance of dangerous intersection, the first step would be one of information, obtaining better observations to shrink uncertainties. Because accurate predictions depend on data, the calmest and most effective response is always more measurement. Only with certainty would higher stakes options be considered, and those would be decided by expert panels whose work is built on the same slow, methodical logic we've followed through these pages. As we close this chapter, picture the serene hum of computers running simulations, stars reflected in the screens, and teams of scientists cross-checking results like gardeners pruning a peaceful hedge. Each rerun narrows uncertainties and strengthens our confidence. The worst-case shapes that fear sometimes conjures dissolve under the patient light of measurement and mathematics. In the next chapter, we will gently explore the cultural and psychological aspects of cosmic risk, why humans imagine dramatic scenarios, how media and storytelling amplify them, and how calm, transparent science restores perspective. Chapter 8: Stories We Tell the Night. Psychology, Culture, and the Need to Imagine Worst-Case Scenarios. As we breathe slowly and let our minds drift with 3I/ATLAS, it is natural that our thoughts sometimes wander from facts into feeling. The sky has always been a mirror for the human imagination. Constellations are stories, comets have been omens, and bright meteors were once messages from the gods. Tonight, as we consider the idea of a visitor from another star, it helps to understand why our minds conjure dramatic what-ifs, and why that impulse can both protect and unsettle us. First, imagine a quiet living room on a cool evening. A parent points out a streaking meteor to a child. The child gasps, tiny fleeting spectacle, and asks, "Will it fall here?" That simple question embodies two human instincts: curiosity and caution. Curiosity drives us to learn. Caution helps us prepare. When we do not yet know the full answer, the mind tends to fill in the blanks with stories. This is the seed of worst-case imagining, a very human tendency to prepare for threats, born from evolution and refined by culture. There are a few gentle, important ways our minds create dramatic scenarios. One is what psychologists call the availability of images. Vivid, recent, or emotionally charged stories are easiest to recall. Dramatic headlines, cinematic portrayals of crashing asteroids, and old tales of doom all sit near the surface of our imagination. When we hear about an interstellar comet, those images can spring forward quickly, even when the data says the risk is tiny. This is not a flaw. It is a safety mechanism misapplied in a time of abundant information. Another common pattern is the emotional pull of singular events. Large, rare events like a planetary impact are memorable and carry symbolic weight. They change history in dramatic ways. Because they would be so consequential, our attention focuses on them, sometimes at the expense of more probable, mundane outcomes. In other words, we give extra emotional weight to rare catastrophes because if they happened, the consequences would be enormous. The result is a mind that lingers on improbable scenarios, while the careful work of probability quietly does its job elsewhere. Media and storytelling then shape the feeling around such events. Sensational headlines, movie scores, and dramatic visuals sell attention. They prime our expectations and can amplify anxiety. But there is another, more gentle role that stories play. They help communities process uncertainty. Folktales and modern documentaries alike let us rehearse survival and moral choices in a safe space. The same story that sparks fear can also seed resilience, dialogue, and curiosity. The key difference is how the story is framed, as panic or as a path to understanding. Here is a small, calm scene to hold in your mind. A community centre organises an evening of stargazing after local scientists give a talk about 3I/ATLAS. People bring blankets and tea, children ask careful questions, and elders remember comets from years gone by. The scientists explain probabilities in gentle language, showing simulations as soft, coloured clouds on a screen. After the talk, a quiet conversation unfolds. Worries are addressed, facts replace rumour, and curiosity is rewarded with understanding. This kind of communal exchange is one of the best remedies for fear. Information shared slowly and kindly, with room for wonder. There are also constructive uses of worst-case thinking. Preparedness is an expression of care. Thinking through dire scenarios can motivate better monitoring, improved communication, and investment in research. The difference between useful preparedness and harmful alarm lies in balance. Plan calmly, based on evidence, and avoid amplifying fear beyond what data supports. Scientists and emergency planners use the same mindset you do when you check a weather forecast and decide whether to bring an umbrella. It is not fear, it is sensible planning. Trust and transparency play a quiet but powerful role in easing collective anxiety. When scientists share how they measure or model an object, when they explain uncertainties and what new observations will reduce them, the public can follow the reasoning. Open data, public briefings, and patient explanations turn unknowns into manageable questions. The more the scientific process is visible, the less space there is for rumour to grow into fear. Imagine watching a slow, careful narrative unfold on a projector as measurements refine a comet's path. Each night the cloud of possibilities narrows and the community breathes easier. Art and ritual also help. Poets, musicians, painters, and filmmakers have long translated cosmic scale into intimate feelings. A lullaby about the night sky, a painting of a comet's tail stretching like a river of light. These works help us feel small in a comforting way, connected to the vastness, not threatened by it. Rituals too can center anxiety. A simple nightly practice of stargazing, a communal reading of the latest science, or a mindful breathing exercise before sleep can transform abstract fear into grounded presence. If we gently return to the question of worst-case scenario, it is useful to hold two truths at once. First, human imagination will naturally explore dramatic possibilities. That is how we learn and prepare. Second, careful science and calm planning guide us toward realistic assessments and effective action. The imagination without data can drift into myth. Data without imagination can miss useful preparation. Together, they form a steady path forward. Before we close this chapter, let us consider how individual actions matter in small, soothing ways. If someone feels anxious about 3I/ATLAS, they can take steps that are both practical and calming. Seek out reliable updates from scientists, join local stargazing events, talk about concerns with friends, and practice grounding activities like slow breathing or mindful observation of the sky. These choices do not eliminate uncertainty, no one can do that, but they transform anxiety into curiosity and agency, as a gentle promise of what lies ahead. In the next chapter, we will explore the technological side of preparedness, the planetary defense tools and strategies humankind has developed to detect, track, and, if ever needed, mitigate potential cosmic hazards. We will examine these technologies not with alarm but with calm curiosity, understanding what is possible today and what might be considered in the distant future. Now let your breathing slow, and imagine a night where a small comet traces a pale arc across the sky, a quiet reminder of scale, and an invitation to both curiosity and calm. Chapter 9. Quiet Guardians, Planetary Defense Detection and the Tools for the Unlikely. As we continue our gentle exploration of 3I/ATLAS and its most unlikely paths, let us rest for a moment in the reassuring fact that humanity has built systems to watch the sky and plans, careful, thoughtful and slow-moving, to respond if the improbable ever became real. This chapter is a calm tour of those systems, how we detect objects, how we measure risk, and what options exist on the shelf of ideas for changing an object's path. We will speak plainly, avoid sensationalism, and keep the focus on measured capability rather than alarm. Detection and tracking are the first and most powerful line of defense. Think of observation as the practice of patient attention. Wide-field survey telescopes sweep the heavens night after night, producing catalogues of moving points of light. When a new object appears, its positions are measured precisely and shared with the global scientific community. The more measurements we collect over time, the narrower the uncertainty about its future path becomes. In those early hours and days after discovery, scientists treat each new observation like a gentle tightening of a rope. With every pull, the picture becomes clearer and calmer. Beyond wide surveys, specialized telescopes perform follow-up observations, photometry to determine brightness and rotation, spectroscopy to learn composition, and radar, when possible, to map shape and size. Radar observations in particular can reveal a lot about an object's surface and motion when the geometry is favorable. All these data feed into simulations and ensembles that produce probabilistic forecasts, giving decision-makers a clear idea of what is likely and what is truly rare. Now imagine that the worst-case probability climbs into a range that requires planning. What tools do scientists and engineers consider? There are a few main approaches, each suited to different sizes, distances, and time-available windows. They are not magic. They are methods rooted in physics, developed slowly and tested where possible. We will explore them one by one with careful language and a calm frame of reference. 1. Kinetic impactors, a gentle nudge at scale. A kinetic impactor is a heavy object sent to collide with the target, changing its momentum slightly. The idea is simple and elegant. A timed, precise hit alters the target's velocity just enough so that, over months or years, the small change grows into a meaningful shift in where the object will be when it would otherwise cross paths with Earth. This technique was tested in recent decades in a controlled experiment, where a deliberately planned collision altered an asteroid's motion in a measurable way. The takeaway is reassuring. Small changes applied early can have large benign effects later. Kinetic impactors are most effective when there is sufficient lead time. The more time before a potential intersection, the smaller the required intervention. 2. Gravity tractors, patience, and the pull of attraction. A gravity tractor is a spacecraft placed near the object that uses its own gravitational pull as a steady, minuscule tug. Over time, this gentle force adjusts the object's trajectory. It is not dramatic. It is meditative. The strength of the tractor grows with time. It is only useful when missions can be planned well in advance. It is also reversible and highly controllable, making it an appealing option when caution and precision are paramount. 3. Fragmentation and dispersion, and why it is usually avoided. Breaking a dangerous object into many pieces may seem like a solution, but it often creates complex challenges. Small fragments tend to spread out and can produce many meteors and small impacts rather than a single predictable event. For most scenarios, fragmentation increases uncertainty, and therefore is approached only as a last resort. After careful modelling shows it would reduce risk rather than multiply it. 4. Non-kinetic methods, radiation pressure and surface alteration. If an object has a volatile surface, small changes, like coating part of it or using focused energy to vaporize surface material, can change how sunlight pushes on it, producing a tiny but cumulative change in motion. Like other methods, these require time, precise knowledge of the object's physical properties, and careful modelling. They are subtle and slow, but in the language of celestial mechanics, slow is often powerful. 5. Nuclear options, a sober last resort. In the spectrum of ideas, using an explosive device is the most forceful and most complex. Historically, such options are discussed only when all other methods are unavailable, and an imminent large-scale threat is confirmed with high confidence. Specialists emphasize that any consideration of these options would be governed by international law, coordination, and extreme caution. Even then, the goal would be to alter a trajectory rather than to cause uncontrolled fragmentation. Because this topic carries legal, ethical, and technical weight, scientists frame it as a theoretical capability to be understood and, if possible, avoided through earlier, less risky interventions. Throughout each of these options, two themes recur: time and information. The earlier we detect and measure an object, the more choices we have and the less forceful those choices need to be. Information reduces uncertainty, and uncertainty drives the need for stronger, less desirable options. Thus, investment in surveys, follow-up telescopes, and international data sharing is both calming and practical. Better observation gives better, lower-risk choices. Coordination and governance are the social elements of planetary defense. Monitoring happens globally. Responses would be international. Scientists, space agencies, emergency managers, and diplomats would all have roles. Communication plans, public advisories, and clear, transparent sharing of probabilities are part of a measured response. When people are informed with calm clarity about what is known and what is not, communities can make sensible decisions without panic. It is worth imagining these teams working together in quiet rooms, exchanging data, and quietly rehearsing responses so that if action were ever needed, it would be deliberate and proportionate. Finally, consider the human-centered side of preparedness. Early warning systems also protect against smaller, more common events, near-Earth asteroids and natural meteor storms, and the same infrastructure that watches for rare interstellar visitors benefits day-to-day planetary safety. Investments in observation pay a double dividend: scientific discovery and improved resilience. As we close this chapter, Picture the slow hum of mission control, engineers reviewing precise trajectories, and scientists sharing models over steaming mugs. The possible interventions are tools in a calm, rational toolbox, not triggers for alarm. Importantly, for 3I/ATLAS specifically, the data and simulations discussed in earlier chapters keep the most plausible outcomes in the realm of safe passage. The existence of planetary defense measures simply adds a further layer of reassurance. If the improbable ever shifted toward plausibility, the world has thought ahead in quiet and methodical ways. In the next chapter, we will gently model a hypothetical worst-case sequence, not to frighten, but to understand step by patient step how unlikely events would be detected, modelled and handled by scientists and authorities. We will walk through that scenario as if following a slow, unfolding drama, always emphasising data and calm response. Chapter 10. A Slow Unravelling. Walking through a hypothetical worst-case sequence. Tonight, we will walk slowly and carefully through a single imagined sequence, a worst-case scenario built not from sudden catastrophe, but from many tiny hypothetical misalignments. The purpose of this exercise is not to frighten, but to illuminate the chain of observation, analysis, and response that would unfold if rare things began to line up. As we move through this scenario, take a deep, calming breath and allow yourself to follow each quiet step. It begins with the first subtle signs, anomalous measurements. Telescopes around the world track 3I/ATLAS night after night, publishing precise positions. Normally, these measurements converge, confirming the comet's safe trajectory. In our imagined scenario, a few measurements, perhaps influenced by a faint background star or a minor calibration issue, produce a slightly different orbit. The cloud of possible future positions stretches just a little, with a faint tail nudging closer toward Earth. Scientists notice this tail and mark it for extra observation. Nothing dramatic happens yet. The proper response in this phase is patience. More nights, more telescopes, careful verification. Follow-up observations then arrive, and the process continues. Observatories increase their cadence, radar teams attempt detailed mapping if geometry allows, and infrared spectrometers search for subtle changes in outgassing. As new data come in, the anomaly either disappears, explained by earlier measurement noise, or it persists. In this imagined path, it persists just enough that a small set of plausible orbits includes a very low probability approach to Earth. Still, the probability remains tiny. Yet, prudence guides preparation, and advisory groups begin sharing updated uncertainties with partners, quietly planning for every possibility. Now imagine a faint secondary source of light appearing near the comet, a tiny fragment, a puff of dust, or an asymmetric brightening of the coma. Analysis suggests that a section of the nucleus has shed material, a common process as comets warm under the sun. Fragmentation introduces dispersion. Each piece may travel with slightly different velocities. Modelers incorporate these fragments into simulations, sampling a range of sizes and speeds. The result is a broadened cloud of possible paths, with a very small number intersecting Earth. The probability remains tiny, yet the scenario now contains multiple moving parts, each accounted for with careful attention. Time begins to matter. Small changes in velocity, applied months in advance, can deflect fragments easily. Days before a potential intersection, far more force would be required. In our scenario, the potential approach occurs weeks to months away. Every extra night of observation significantly reduces uncertainty. International observing campaigns are activated, telescopes coordinate around the clock, and simulation groups rerun ensembles with fresh inputs. The atmosphere remains calm and professional. This is measurement, not drama. Advisory bodies then convene: astronomers, mission planners, and emergency managers. They interpret probabilities and consequences, not absolutes. Public communication is measured, emphasizing what is known, what remains uncertain, and the steps being taken to learn more. The initial messages highlight the low probability and the strategies in place to reduce uncertainty. Transparent updates help the public understand without panic and direct attention toward constructive curiosity rather than fear. If simulations suggest a non-negligible chance of a damaging fragment, experts consider mitigation. Feasible options depend on fragment size and available lead time. Kinetic impactors, gravity tractors, or non-kinetic surface alteration methods require months or years to deploy. In our scenario, lead time is modest, so planners focus first on observation while preparing a targeted small mission concept to nudge a fragment if absolutely necessary. Decisions remain methodical, conservative, and measured, waiting until uncertainty decreases and risk increases before intervention. Parallel teams model atmospheric entry dynamics for plausible fragment sizes. Most are small, pebbles or boulders, and would disintegrate high in the atmosphere, creating air bursts or meteor showers. Larger fragments, city-scale in size, are far less likely, yet modelled thoroughly. Potential impact zones, energy deposition, and local infrastructure effects are all analysed. Planning emphasises prudence and compassion, focusing on protecting populations while understanding that most outcomes remain benign. International coordination and legal considerations are quietly woven into the process. Any mission to alter a celestial object involves shared resources and legal protocols. Diplomats, legal advisors, and technical teams ensure ethical restraint and transparent decision-making. Collaboration reinforces trust and maintains a careful, measured approach, avoiding unilateral action or rash responses. If intervention becomes necessary, it is executed with precision. A minimal kinetic nudge would be designed to slightly alter velocity, ensuring fragments miss Earth months later. Continuous observation confirms the effect, narrowing the cloud of possibilities. The process is deliberate, calm, and guided by physics, a quiet efficacy rather than dramatic spectacle. Finally, after the risk passes naturally or through intervention, reflection begins. Scientists collect data to refine models of fragmentation, outgassing, and orbital dynamics. Detection methods are improved to allow greater lead times for future interstellar visitors. Communities receive clear information and, if needed, local support. The long-term outcome is a strengthened patient capacity to manage rare cosmic events, turning uncertainty into knowledge. Throughout this imagined scenario, notice the emphasis on observation, measurement, transparency, and international cooperation. Even in a sequence of unlikely events, careful, patient action guided by evidence transforms a hypothetical worst case into manageable steps. Picture the scene. Scientists awake in overlapping time zones, sharing notes through slow emails and video calls, telescopes exchanging photons like carefully penned letters, simulations running through the night. The world observes not with fear, but with disciplined curiosity. And as the comet continues along its distant path, the cloud of possible futures gradually narrows, like the dawn quietly erasing the stars one by one. Chapter 11. Watching Together. Public engagement, education, and quiet ways to participate. As our exploration of 3I/ATLAS continues, let us turn gently to the ways people everywhere can participate in this quiet global story. Science is not only done in observatories and mission control rooms, it grows richer when curious minds and patient hands around the world join in. This chapter is about how communities, classrooms and individuals can engage responsibly, learning, contributing, and finding calm in the craft of observation. First, understanding what to listen for is comforting. When astronomers detect an unusual object, they release straightforward updates. Where it is in the sky, how bright it appears, what telescopes are observing, and whether its path poses any concern. These updates are meant to inform, not alarm. A useful practice for anyone feeling anxious is to rely on primary, reputable sources, local observatories, science institutions, and educational outreach programs, rather than the first headline that demands attention. Over time, you'll notice a pattern. Scientists share uncertainty honestly and update calmly as more data arrive. That steady cadence is a practice we can all adopt in our daily lives. There are many simple, peaceful ways to participate. Amateur astronomers and backyard observers provide valuable follow-up observations that professional surveys sometimes miss. A small telescope or even binoculars can reveal a faint, hazy patch of light to someone who has learned where to look. Citizen science platforms also invite people to help classify images, measure brightness, or log observations. These tasks are easy to learn and deeply rewarding. You become part of the process that turns scattered photons into scientific knowledge. If you live near a community observatory or planetarium, consider attending a public night. These events are designed to share the sky in gentle, accessible ways. An expert will often explain what instruments are doing, point out the comet through a telescope, and answer questions in patient, plain language. For families, this can be a ritual, an evening of shared curiosity, where children learn how to ask careful questions and adults remember how to wonder without panic. Schools and educators have a special role. A lesson about 3I/ATLAS can be a quiet interdisciplinary journey. Physics for motion and gravity, chemistry for comet composition, history for how cultures interpreted comets, and art for translating the experience into drawing or music. Projects can be calming and creative. Chart the comet's position across the week, write reflective journals about the feeling of looking up, or create simple models that show how light and heat cause a comet's tail to form. These activities build scientific literacy and teach the measured approach of asking, observing, and updating beliefs based on evidence. Media literacy is another gentle skill to cultivate. When a dramatic image or headline appears, ask 3 quiet questions. What is the source of this information? Is there a measure of probability or uncertainty included? What do scientists directly involved say? These 3 steps help turn reactive fear into thoughtful curiosity. Over time, practicing them creates a more peaceful relationship with news and a better ability to separate sensationalism from sober assessment. There are also safe, joyful ways to observe natural effects like meteor showers. If a comet fragments and creates a stream of debris, Earth may pass through that stream and produce an increase in meteors. Watching a meteor shower is a slow, restorative activity. Lay back on a blanket, breathe slowly, and let the occasional streak of light puncture the wide dark. These moments connect us to cosmic time without threatening immediate danger. For many, they become rituals of wonder and gratitude. A small, calm anecdote. Imagine a retired math teacher who volunteers at a local observatory. On a clear night, a family arrives. A child curious about the glowing patch their parents saw in a news clip. The teacher points the telescope, adjusts the focus, and together they watch a distant, fuzzy visitor. The child asks simple, earnest questions. The teacher responds with quiet facts and gentle metaphors, explaining how scientists measure position and brightness. Afterward, the child falls asleep in the car with star-bright eyes, and the parent feels steadier, reassured by the patient clarity of explanation. This is the human side of scientific engagement. Small encounters that replace worry with understanding. Volunteer networks also do practical things that matter. Amateur radio operators help coordinate communications in outreach events. Local astronomy clubs maintain small telescopes and guide visitors. Makerspaces build simple detectors and teach students how to log observations. Each small activity strengthens public understanding and contributes data or attention that professional teams value. In this way, the response to 3 I/A-T-L-A-S becomes a shared cultural moment, an exercise in community learning rather than a cause for alarm. For those who wish to go a step further, learning basic sky skills is surprisingly soothing. Learn to find Polaris or another consistent star, understand how the moon's phase changes, and practice identifying bright constellations. These skills orient you in the night and remind you that many celestial patterns are predictable and benign. When an unusual object appears, you have a calm framework from which to ask questions and follow reliable updates. Finally, keep in mind that curiosity and calm are practices you bring home. If the idea of cosmic risks feels heavy, translate that energy into something constructive. Volunteer at a local science centre, attend a public lecture, or start a small stargazing group with friends. Shared curiosity turns fear into connection, and connection turns abstract worries into tangible, manageable learning. As we end this chapter, picture small groups of people scattered across the globe. Neighbours on rooftop terraces, school children with paper star charts, elderly volunteers guiding curious visitors, all participating in a quiet, collective act of observation. The comet passes through once, but the knowledge and mutual trust built in these moments last much longer. Each calm conversation, each measured question, helps the world respond to the rare and the unusual with grace. Chapter 12. What past cosmic encounters teach us. Humanity's relationship with the sky is threaded through history. For thousands of years, people watched comets and meteors and wove them into stories, calendars, warnings, and art. Those stories are not just superstition. They are records of how people paid attention to rare events, how communities organized, and how practical knowledge accumulated over generations. Tonight we listen to those echoes not to alarm ourselves, but to learn. How did people respond to unusual sky events in the past, and what parts of that wisdom still help us today? When a bright comet appears, people take notice. In some traditions, comets were portents. In others, they were curiosities to be recorded in meticulous annals. Those early records became data, descriptions of brightness, colour and motion that modern researchers can sometimes use to corroborate astronomical events from centuries ago. The key lesson is the power of careful observation. Even without sophisticated instruments, human eyes and patient note-keeping built a long, useful archive of cosmic behaviour. There are also practical lessons from more recent history. Local communities who witnessed dramatic meteor events learned immediate survival and communal response techniques. Stories of aiding those affected by localized impacts, clearing debris, and coordinating shelters remind us of the value of preparedness at a small scale. These are not dramatic procedures. They are neighbourly acts. Check on one another, provide food and warmth, and record observations to help experts later. The humane, slow responses of communities are as important as any technical fix. From a scientific perspective, past encounters taught us about impact mechanics, airbursts, and the distribution of debris. Observations and recovered fragments allowed scientists to understand composition and entry behaviour. Those lessons shaped modern atmospheric entry models and emergency protocols. In short, history shows that observation plus small, rational responses reduce harm more effectively than panic. A quieter lesson from history is humility. Human cultures kept many cosmologies that framed rare sky events in moral or mythic terms. They also created rituals to soothe anxiety, shared meals, communal storytelling, and periods of reflection. Those rituals helped people process uncertainty together. Today, we can borrow that communal calm. Clear information paired with quiet community rituals, a town meeting, a public stargazing night, a classroom lesson, help transform abstract fear into concrete shared experience. So tonight, as 3I/ATLAS drift past, we listen to past wisdom. We practice careful watching, neighbourly care and patient learning. The past teaches us that collective attention, humble inquiry, and a willingness to help one another make the present safer and more humane. Chapter 13. The Physics of Impact. Airbursts, Cratering, and Why Scale Matters. To understand any worst case, we must understand the physics of impacts, how objects interact with planetary atmospheres and surfaces. This chapter is a slow, intuitive guide to why small differences in size, speed, and composition change outcomes dramatically, and why most fragments from a comet like 3I/ATLAS are more likely to create bright meteors than global catastrophe. When a small particle, a speck of dust or a pebble, enters an atmosphere, friction and pressure heat it quickly. Most of these particles vaporize high above the ground, producing the familiar streaks of a meteor shower. These events are beautiful and harmless in human terms. They're a reminder of the constant benign interactions between Earth and the debris that drifts through space. Larger fragments behave differently. A boulder-sized piece will decelerate as it pushes through the air, and the pressure can cause it to fragment or explode in the sky, producing what scientists call an airburst. The energy release can be dramatic locally, a bright flash, a shock wave, perhaps shattered glass several kilometers away. But the effects tend to be localized. Because the atmosphere absorbs much of the energy, widespread global effects are uncommon unless the object is very large and dense. The most severe outcomes, crater-forming impact or climate-altering injections of dust into the stratosphere, require very large objects. These are rare in the cosmic lottery and involve sizes and energies vastly different from the small fragments that typically accompany comets. The difference between a harmless meteor streak and a globally consequential impact is not linear, it is exponential. This is an important counterpoint to alarm. The universe produces many small events, and very few truly catastrophic ones. Composition matters too. A porous, icy fragment behaves differently from solid metallic rock. Ice and porous aggregates tend to fragment higher and release energy over a wider area, reducing the potential for concentrated ground damage. Dense, iron-rich fragments are more penetrating and can reach the surface with more residual energy. Scientists use knowledge of material behavior, gathered from past meteor recoveries and laboratory experiments, to model these interactions calmly and thoroughly. Finally, consider geographic distribution and infrastructure. A localized impact in an uninhabited area is a very different social event from an airburst over a densely populated region. Emergency planners therefore model not only physical effects, but also population vulnerability. This layered approach, combining physics with human geography, produces the most useful assessments and the most compassionate plans. As you breathe slowly now, imagine the sky filling with harmless shooting stars, and remember the gentle truth we've seen here. Scale and material govern outcomes. Most cosmic debris makes only beautiful fleeting streaks. Truly disastrous events require a chain of unlikely conditions. Chapter 14. Could an interstellar comet change the world? A natural worry is whether an interstellar comet could trigger longer-term environmental or climatic effects. The good news, which we will explore now, is that only very large impacts, rare by every measure, can change climate or biosphere dynamics in lasting ways. Smaller fragments, even if they produce local damage, are unlikely to cause planetary-scale changes. To affect global climate in a lasting way, an event must inject substantial amounts of dust and soot into the upper atmosphere, where it can persist and block sunlight for months or years. This can cool the planet and disrupt ecosystems. The geological record shows that such events have happened in Earth's deep past, but they are separated by very long timescales. In practical modern terms, for a single cometary fragment to cause comparable effects would require an object far larger than the fragments typically associated with comets like 3I/ATLAS. There are also biological considerations. Could extraterrestrial material carry pathogens or otherwise harm life on Earth? The scientific consensus is cautious but reassuring. Space is a harsh environment for life as we know it. Radiation, vacuum, and extreme cold make survival during interstellar travel difficult. Moreover, Earth's atmosphere and biosphere are robust filters. Most incoming material vaporizes before it reaches the surface. Planetary protection protocols exist mostly to govern spacecraft and scientific sampling, ensuring we proceed with care in the unlikely event of direct sample return. In sum, biological risk from a passing comet is exceedingly low. Another subtle angle is the potential for comets to deliver beneficial material. Throughout Earth's history, impacts have contributed organics and water, components that may have helped life emerge. From that perspective, comets are also bearers of building blocks. For 3I/ATLAS, which shows signs of organics, the theoretical discussions centre on possibility and curiosity rather than danger. Finally, environmental resilience matters. Human systems are adaptable. Modern weather forecasting, infrastructure planning, and international coordination mean that local effect can usually be managed and recovered from. The global supply chains and communication networks we rely on are also strong supports in responding to localized impacts. In other words, society's capacity to respond reduces the effective risk to long-term biosphere stability. As you let your breath deepen, picture Earth's atmosphere as a careful protective layer, filtering, buffering, and making the planet robust to most small cosmic intrusions. The natural rhythms of the biosphere continue, and the passage of a comet is an occasion for wonder and scientific learning more than an environmental crisis. Chapter 15. From Curiosity to Capability. How 3I/ATLAS could improve our readiness. One of the most comforting outcomes of unusual astronomical visitors is that they spur improvement. Even when they pose no real danger, they become catalysts for better telescopes, improved data sharing, and refined models. Let us turn gently now to how the passage of 3I/ATLAS could enhance humanity's capabilities, making us better prepared for truly rare events in the future. First, observation networks grow stronger. The coordinated campaign to observe an interstellar visitor tests logistics. Who points which telescope when, how images and spectra are shared, and how simulation groups integrate fresh data. Each successful coordinated night becomes a rehearsal and an upgrade of infrastructure. Telemetry pipelines get faster, instruments are retooled for follow-up tasks, and software for orbit fitting improves. These are small, practical gains that matter when time is short. Second, instrumentation benefits. Interest in interstellar objects encourages investment in new detectors and survey strategies. For example, wide-field surveys may tweak cadence or image processing algorithms to catch fast-moving faint visitors earlier. Spectrographs and infrared instruments get tuned to detect specific molecular bands. Investments that begin as curiosity-driven research often become routine improvements in planetary defense and astronomy. Third, modelling and simulation sharpen. The experience of running ensembles on a real, complex object teaches modellers about fragmentation, non-gravitational forces and observational systematics. That knowledge feeds back into future risk assessments, making models more realistic and their uncertainty estimates more trustworthy. As a result, decision-makers get clearer guidance in shorter timeframes. Fourth, the human systems improve. International collaboration, public communication strategies, and emergency protocols are exercised. Coordination between observatories, space agencies, and civil response organizations becomes more practiced and more efficient. These procedural upgrades matter because effective response is as much about organization as it is about technology. Finally, public interest fuels education and recruitment. A widely followed sky event inspires students and amateur scientists. Young people who watch a comet through a classroom telescope may choose to study physics, engineering, or atmospheric science. In this way, curiosity becomes the seed of future capability. As you relax, imagine the quiet ripple effect. A comet passes, telescopes hum, students take notes, engineers refine instruments, and a small but meaningful strengthening of global readiness takes place. What began as a brief visitor becomes a long-term gain for science and safety. Chapter 16: Rules of the Quiet Sky, International Law, Governance, and the Ethics of Intervention. As we continue to follow 3I/ATLAS on its serene passage, we arrive at a gentle but important subject: how nations, scientists, and citizens agree on what to do, or not do, when an unusual object crosses our skies. This chapter explores the frameworks that guide action, the legal treaties, cooperative institutions, and ethical principles that shape any decision about observation, communication, and intervention. We will treat these topics with calm clarity, because rules and values help us act wisely rather than react out of fear. At the broadest level, space is governed by a set of shared norms and treaties born in a spirit of collective stewardship. These instruments are designed to preserve space as a global commons, a place for peaceful use, for science, and for the benefit of all humanity. When unusual visitors like 3I/ATLAS arrive, those shared expectations are the first, quiet foundation for how the world responds. They remind us that no single country or agency owns the sky, and that cooperation is both a moral and practical necessity. Practical governance of an event begins with transparency and data sharing. Scientists worldwide rely on open exchange because better information produces better decisions. Observatories post measurements, researchers circulate refined orbits, and modelling groups share ensembles and uncertainty ranges. This cooperative cadence is not merely polite, it is protective. The most effective actions are those taken on the basis of broad, independently verified data, and international practice has evolved to encourage exactly that. When policymakers and technical experts evaluate whether to move from observation to intervention, several questions frame the conversation. Is the probability of harm above an agreed threshold? What is the best available estimate of object size, structure, and composition? How much lead time exists to act? Who has the technical capability to act, and under whose authority would that action proceed? These questions are answered not in isolation, but through structures of consultation and review that prioritize clarity, shared responsibility, and accountability. Ethics plays a central role here. Even the possibility of intervening with the celestial body raises profound questions. Who decides on actions that affect planetary safety? How do we weigh the risks of intervention against the risks of inaction? Which populations should be consulted if an impact might affect a particular region? Ethical governance asks us to act with humility, to favour reversible and minimal interventions whenever possible, and to protect vulnerable communities through transparent planning and equitable support. Multilateral coordination mechanisms embody these ethical commitments in practice. International scientific bodies provide foray for technical review, while diplomatic channels enable legal and policy coordination. In a calm response, scientists present data to advisory groups. Those groups discuss probabilities and options. Diplomats and relevant agencies consider legal, environmental, and societal implications, and a consensus recommendation, if any, is advanced. The aim is not unanimity for its own sake, but a process that respects voice, expertise, and the shared stakes of Earth's inhabitants. A quiet but crucial legal concept to keep in mind is responsibility and liability. Activities in space can have consequences on Earth, and international norms increasingly emphasize that actors must consider harm and take reasonable precautions. Any deliberate intervention, for example, launching a deflection mission, would therefore be accompanied by careful legal review, coordination agreements, and commitments to transparency. The goal is to avoid unilateral moves that might create diplomatic friction or unintended physical effects. In other words, law and diplomacy are practical tools that reduce risk by ensuring actions are deliberated, proportional, and cooperative. Planetary protection is another ethical consideration woven through these deliberations. Scientists balance the desire to learn from extraterrestrial material with the responsibility to avoid harmful contamination, both of Earth and of other celestial bodies. Although a passing comet like 3I/ATL-AS is unlikely to necessitate strict containment measures, the principle reminds us to behave as careful custodians. Sample return missions, for example, follow strict protocols to prevent biological cross-contamination. This ethic of care extends to public communication as well. Information should be shared honestly and with sensitivity to diverse audiences. Transparency in communication deserves its own quiet emphasis. When authorities convene to assess risk, they also plan how to inform the public. Ethical communication avoids sensationalism while acknowledging uncertainty. It presents probabilities plainly and summarizes what actions are being taken to reduce uncertainty. The calmest institutional responses are those that keep communities informed at each step. What data have been collected, what the simulations show, and what thresholds would prompt further action. This openness builds trust, and trust is the social lubricant that keeps communities steady in the face of rare cosmic events. Another aspect of governance is technical preparedness and equitable access. Not all nations have large observatories or space launch capabilities, yet all are affected by decisions about the sky. Ethical governance therefore includes capacity building, sharing data, offering collaborative observation opportunities, and providing technical assistance to nations that otherwise might be excluded. In this way, the global response to 3I/ATL-AS is not only about protecting Earth, but about honouring a shared claim to the night sky. Let us gently imagine a decision pathway that honours these principles. First, scientists gather and share data openly, refining the comet's orbit and physical properties. Second, international technical groups review the ensembles and summarize probabilities in accessible language. Third, diplomatic and legal advisors consider the international implications and prepare joint statements. Fourth, communities and local authorities are informed about possible scenarios, with guidance for practical preparedness if necessary. Finally, if an intervention becomes warranted, it proceeds under a multilateral framework, using the least intrusive, most reversible method available and accompanied by transparent monitoring and assessment. Each step pauses for evidence and for the voices of diverse stakeholders. It is also useful to consider how norms evolve. Past practice informs present law, and present experiences shape future treaties. The passage of unique visitors like 3I/ATLAS becomes a learning opportunity. What legal gaps emerged? How did governance perform? What improvements are needed to ensure fairness, clarity, and ethical rigour next time? Over the long view, these small refinements make the international system more robust and more humane. We close this chapter with a quiet affirmation. The sky may be vast and indifferent, but human responses need not be. Through law, shared norms, and ethical reflection, we can ensure that our reactions to rare cosmic visitors are guided by reason, care, and cooperation. This is how communities sleep more soundly at night, knowing that thoughtful institutions exist, that data guide action, and that the default posture is transparency, humility, and shared responsibility. Chapter 17. From Idea to Launch: How a Deflection Mission Would Be Designed and Executed. In the very rare and unlikely event that observations and simulations suggested the need for intervention, the world would move gently from calm measurement to careful engineering. Designing and launching a deflection mission is never rushed. It is a slow and deliberate process, shaped by time, by information, by international consent, and by technical feasibility. Tonight we will walk through that process step by step, not as an alarm but as a clear and steady map of how reason, cooperation, and engineering transform uncertainty into manageable choices. The very first question is always simple: do we have enough information to act? Advisory bodies consider probabilities and consequences together. Has the chance of an encounter risen above a pre-agreed threshold, and are the potential consequences significant enough to justify a mission? If the answer is no, observation continues with even greater intensity. If the answer is yes, then planners move forward carefully into mission studies. This restraint is essential because premature action could waste resources, undermine trust, and create unnecessary risks. Once the decision to plan is made, the next step is to define the mission's objective. The goal is always narrow and precise: to change the object's velocity by the smallest amount necessary so that its trajectory shifts just enough to avoid Earth. Success is defined in measurable terms, a detectable change in the object's motion that, when projected into the future, reduces the probability of impact to below the level of concern. By keeping goals simple and verifiable, the mission becomes both technically achievable and ethically responsible. With the objective clear, engineers then choose an approach. The method depends on three things: the amount of time available before a possible encounter, the size and composition of the object, and the assessed probability of impact. If there is ample time, months or even years, gentle methods such as gravity tractors or small kinetic nudges are often sufficient. If time is short and the object is small, a direct kinetic impactor may be the preferred choice, a spacecraft designed to collide with the body and impart momentum. If the object's surface properties are well understood, other methods such as focused energy to alter outgassing might be considered. Each option carries trade-offs in complexity, risk, and international acceptance. Every mission then takes shape around a common set of architectural choices: spacecraft mass, propulsion type, navigation systems, sensors, communications, and safety margins. A kinetic impactor must carry robust guidance to strike a small, possibly tumbling target. A gravity tractor must be designed for precise station keeping and long-term thrust control. Rendezvous missions require careful budgeting of fuel and propulsion, while simple intercepts prioritize speed and accuracy. Propulsion is one of the most critical factors. Chemical rockets provide high thrust, ideal for fast transfers and quick response. Electric propulsion, such as ion engines, offers higher efficiency but demands more time to reach the target. Designers weigh launch windows, required changes in velocity, available rockets, and flight times. The lesson is always the same. Earlier detection leads to simpler missions, because more time means gentler, more flexible options. Perhaps the most delicate challenge is guidance and control. Striking or rendezvousing with a small object millions of kilometers away requires extraordinary precision. Missions combine ground-based tracking, onboard cameras, and autonomous navigation algorithms. Optical systems guide the spacecraft as it approaches. Radar and LIDAR refine estimates of distance and shape. In the final moments, autonomous systems take over, adjusting in real time to ensure an accurate intercept. This capability has already been demonstrated in planetary defense experiments, and now forms the backbone of future strategies. Before a launch ever takes place, engineers spend months or years in preparation. Simulations test guidance systems, explore potential failures, and model fragmentation scenarios. Hardware-in-the-loop testing allows the spacecraft systems to run in realistic conditions. Where possible, rehearsal missions or technology demonstrations provide additional confidence. These rehearsals are not dramatic spectacles but quiet exercises in patience, practicing recovery from anomalies, checking international communication protocols, and ensuring that every possible outcome has a plan. The launch itself is an international effort. Agencies, launch providers, and diplomatic channels coordinate permissions, telemetry responsibilities, and public communication. The chosen launch window minimizes risk and maximizes efficiency. Throughout, transparency reassures the global community that actions are deliberate, lawful, and proportionate to the threat. Once in flight, the mission becomes a patient dance of corrections and monitoring. Mid-course maneuvers refine the trajectory using the latest tracking data. If the mission is a kinetic impactor, the final targeting is carried out by autonomous navigation in the last minutes, guiding the spacecraft into a precise collision. If it is a gravity tractor, the spacecraft instead hovers near the object for months, applying a slow, steady gravitational tug. In both cases, data streams back to Earth, where scientists confirm each step with care. After the operation, whether impact or slow tug, the true measure of success is found in the numbers. Follow-up telescopes measure the new trajectory. Radar and optical observations confirm changes in velocity. Scientists recalculate probabilities. If the required adjustment was achieved, risk falls away. If it was not, planners calmly consider whether additional action is needed. Risk management extends even further. Missions are designed with redundancies, with contingencies for partial success, and with scenarios for fragmentation. If a body breaks into smaller pieces, dispersion may reduce danger, turning risk into a harmless meteor display. Every possibility is considered in advance, so that surprises are met with preparedness rather than panic. And then comes the phase of reflection and learning. Every detail of the mission, from engineering choices to diplomatic coordination, is reviewed. Data about the comet's structure, about fragmentation, about guidance performance, all feed back into models and strengthen readiness for the future. International reports refine both technical standards and ethical frameworks, ensuring that future actions remain measured, lawful, and transparent. Through all of this, the guiding principles remain the same: time, information, and proportionality. The more time humanity has to prepare, the gentler the solutions can be. The clearer the information, the more precise the engineering, and every action is shaped by the principle of doing only what is necessary, never more. As you rest, picture the control room where this work unfolds. Engineers sit quietly at their stations, their screens glowing softly. A gentle series of beeps marks the rhythm of telemetry. There is no drama here, only focus, patience, and quiet satisfaction. Somewhere, millions of kilometers away, a small nudge has altered the course of a wandering rock. Months later, that rock will pass harmlessly by. The world will scarcely notice, except for those who remember the long, careful work that kept it safe. Chapter 18. Gentle Preparedness, Local Response, Emergency Planning, and Recovery. Now, as our thoughtful exploration of 3I/ATLAS moves from the realm of orbital paths and spacecraft into the human scale, we arrive at the question of local preparedness. What would communities, emergency managers, and local authorities do if a fragment or debris stream ever posed a localized risk? The answer is not dramatic. It is quiet, careful, and familiar, grounded in the same kind of planning used for storms, floods, or earthquakes. This chapter is meant to reassure. It shows how impact scenarios, however unlikely, would be translated into clear, compassionate actions: mapping, warning, sheltering, recovery, and the small rituals of care that keep people steady. It is worth beginning with a calming reminder. In almost every case, interventions happen long before local action is needed. National and international teams of scientists would first narrow uncertainties and, if necessary, inform civil authorities about possible outcomes, including timing and geographic footprints. Local planners would then take those probabilities and translate them into practical measures, the same way a city translates a weather forecast into sandbags, cooling centres, or detour routes. The difference is one of scale and timing, but the process is not unfamiliar. The first operational step is mapping. Specialists take the best available simulations and generate probabilistic footprint maps, showing where fragments might fall or where an airburst could be felt. These maps are then layered with information about population density, hospitals, power plants, water systems, and transportation routes. Emergency managers use these overlays to identify where resources should be focused. Importantly, the maps display probability gradients, not certainties. This means planners can scale their response. Areas of higher likelihood and consequence receive more preparation, while places on the edge of possibility maintain watchful but routine vigilance. Once maps are prepared, communication begins. Clear, calm warning systems are the backbone of any local response. Authorities would use familiar channels: local radio, emergency alert systems, social media, and community networks, to share updates in plain language. Messages are kept brief and action-oriented: what to expect, where it might happen, and what protective steps to take. The emphasis is always on clarity, not technical detail. For example, stay indoors during a bright flash, move away from windows during a potential shockwave, and follow local instructions if evacuation becomes necessary. Repetition and consistency across trusted sources reduce rumours and prevent fear from spreading unchecked. Protective guidance is then matched to the scale of the event. For most modelled outcomes involving small to medium fragments, the safest and simplest response is sheltering in place. staying inside solid buildings away from windows to reduce the risk of flying glass or falling debris. If ground impacts are possible, targeted evacuations can be planned for the smallest number of people necessary, timed carefully so disruption is minimized. These actions are not sweeping or chaotic. They are precise, deliberate, and focused on keeping life as normal as possible while ensuring safety. Infrastructure protection is also quietly practical. Utility companies can increase monitoring of power and water systems. Hospitals prepare for possible surges in patients. Transport agencies review alternate routes for emergency vehicles and essential deliveries. Fire and medical services pre-position equipment and staff in areas where models suggest effects might be strongest. These adjustments are rarely visible to the public, but they make a profound difference in how quickly a community can recover. Some risks are secondary, yet no less important. A fragment that reaches the ground might spark fires or scatter hazardous debris. Fire services prepare to respond quickly, while public messages remind residents to avoid unfamiliar debris and report it instead. Beyond the physical, planners recognize the psychological impact of such an unusual event. Even if damage is minimal, the experience of a bright flash, a loud boom, or an unexpected headline can leave people unsettled. Local authorities therefore plan for mental health support. Community centres with counsellors, hotlines staffed by trained listeners, and public messages that normalise anxiety while offering grounding practices. In emergencies, emotional care is as valuable as logistical response. When the moment has passed, recovery unfolds in two layers: humanitarian and scientific. Humanitarian recovery focuses on clearing debris, restoring utilities, and supporting affected households. Scientific recovery focuses on collecting and analysing any surviving fragments, turning them into data that improves future preparedness. Universities and museums often partner with local governments to handle such material responsibly, balancing curiosity with safety. This dual process helps transform disruption into learning and gives communities a sense of agency and contribution. Through every stage, transparency remains essential. Authorities that share openly, explaining what they know, how confident they are, and what steps are being taken, strengthen public trust. Simple, predictable schedules for updates prevent rumours from filling gaps. Messages always emphasise practical steps citizens can take, checking on neighbours, keeping pets safe, and following official instructions. In this way, communication becomes not only informative but also unifying. Quiet preparedness also includes rehearsal. Communities benefit from tabletop exercises and small-scale drills that walk officials through decision-making chains without alarming the public. These rehearsals refine contact lists, confirm communication templates, and test logistical plans. By practicing in advance, officials ensure that if the improbable ever does occur, the response will be measured, familiar, and calm. Equity is another cornerstone of resilience. Preparedness plans always include attention to vulnerable populations, people with mobility challenges, limited information access, or language barriers. Shelters must be accessible, warnings must be issued in multiple languages, and transportation support must be arranged for those who need it. Protecting the most vulnerable is both an ethical responsibility and a practical necessity. A community that includes everyone in its safety net recovers faster and more cohesively. For individuals, the advice is gentle and familiar. Keep a small emergency kit with a few days' supplies. Maintain a battery-powered radio for official alerts. Know your community's evacuation routes. Prepare a simple shelter-in-place plan for your household. These steps are the same ones recommended for storms, floods, and earthquakes. They are modest, reassuring habits that turn worry into preparedness and give people a sense of control. Finally, every event, no matter how small, leaves behind lessons. After-action reports, community meetings, and academic studies review what worked well and what could be improved. Each round of learning strengthens the systems for next time, building a deep institutional memory. The comet or fragment passes, but the wisdom remains, ready for the future. As this chapter closes, imagine a calm local command centre, maps glowing on screens, volunteers standing ready at community halls, the soft hum of radios carrying clear instructions, neighbours checking in on one another. The actions are practical, compassionate, and rooted in ordinary human care. Even a rare cosmic brush would be handled by systems designed to reduce harm, restore stability, and strengthen resilience. Breathe in slowly, breathe out gently. Picture your community steady, connected, and quietly prepared, not with fear, but with confidence in small, sensible measures and the enduring strength of mutual aid. This is how human response turns improbable cosmic events into manageable human stories.